Uh, so, so we saw there that to determine the protection potential and the current output, we will need to apply the Ohm's law, which calculates the potential over the resistance. So the resistance, we saw how to calculate it using the resistance equations. Basically, we will focus on the white equation in this course, but anyways, you can take a look on the other equations and try to compute how they look. Uh, and of course, as we saw all the equations for resistance, we identified that the resistivity is an important play. It's not the same resistivity in Gulf of Mexico than Persian Gulf, the North Sea, than in the mud, that in a river or anything like that. So what is the potential? As we saw, the resistivity, the resistance came from resistivity, so it's very important to maintain resistivity. But what about the potential? Which potential do we need to utilize to calculate the Ohm's law? So this potential requirement, remember, when we saw thermodynamics, we identified the potential of protection, as we see there, the cathodic protection, is when we reach potential versus the hydrogen, standard hydrogen electrode of minus 0.6. And then we reach the cathodic protection. For immersing solution, for still immersing solutions which contains active sulfate reducing bacteria, so we need to go a little bit deeper. We need to go there because we are adding an extra reactions there, an extra criticality there with the bacteria. It's important to notice that the diagram here is versus the hydrogen, but we are talking about the minus 800 or minus 900 versus the silver chloride seawater reference electrode. This is the potential to protect the steel, however, is not the potential that we need to utilize there. This is the driving potential, and we will see how to calculate the driving potential. So this is the potential requirement. We need to reach that potential. So the anode should have enough power to reach this minus 600 versus the hydrogen electron. Potential, protection potential, and anode current output. So the final length and final mass are calculated as follows. Of course, we need to know the final length because the Dwight equation requires the final length and requires this final radius of the anode to calculate. However, the Dwight equation is basically calculating the output current after the anode reaches certain service, which is this U factor, utilization factor, is usually 0.85. So the anode is never reaching the 100% over the entire time of the life of the anode. We will utilize this thing to calculate the Dwight equation and to design the system. Current required and protection potential. So the current required is exactly as it shows there. We need to have the current density required, and we need to have the surface area to protect, and we need to have the coating factor. The coating factor is basically all the structures that are submerged or could have, not all the structures, but some of them, they have coating, protection coating. So the coating, if it's a very good coating, then the porosity is very low, and then is the very steel that is the steel that is in contact with electrolyte is reduced. So this coating factor needs to be counted there. In the example we are talking about, we will not analyze a situation where we have a coating structure. So the area came from drawings, and it's considered to be for steel that is exposed to the electrolyte. As I said, it's just the steel that is exposed to the electrolyte. The steel that is not exposed to electrolyte needs to be counted differently. For example, if the bare steel is touching seawater, mud, and then it goes to the air, then we need to count for every electrolyte, we need to consider the area that is exposed to that electrolyte. So the actual cathodic current density is a complex function as we evaluate over the course, in which different things are playing. So the oxygen, the temperature, the composition of the electrolyte, the resistivity of the electrolyte, the pH, and the electrolyte depth. If you remember when we saw the kinetics section, we saw how the current change depending of the conditions. And basically this BSEN 13174 2001 indicates specific values for required to polarize the object to a potential more negative than minus 800 millivolts with respect to silver chloride seawater reference electron, which is the minus 0.6 versus the hydrogen electron.